Welcome, everyone. Welcome to our talk. Hello to everyone watching on stream. We have some colleagues watching, so hello. Zoltan, in particular, he said he would be watching. We have some colleagues over there. Hello. Welcome to our binary coverage talk, where you will learn how to find blind spots in software testing. Don't worry, we'll explain what everything means. First things first, who are we? We are all engineers from SUSE, QA engineers. What that means, our department ensures that the product we create, which is mainly SUSE Linux Enterprise, that it's up to standard. We test it quite a bit. We are looking for bugs. We are trying to break it. And we report bugs to the developers. If you're using SUSE, you can be sure that we made sure that it's a high-quality product. Hello, my name is Emil. I am in the Security QE department at SUSE. I am also a teacher in Prague at the Gymnasium na Keplera, where I teach Linux and all sorts of things. I am a ThinkPad fan. You might have seen my ThinkPad corner over there, and you might know me from my previous talks from previous years about ThinkPads and the sort. We also have Ondra, and we have only one mic, so we have to do this.
Yep, hello. The other mic isn't wired for the room, so we have to speak into this one for all of you to hear us. So my name is Ondřej Pithart. I'm also in SUSE QE, specifically in update validation. As a fun fact, I own 2 BMWs, I guess. We like to work on old cars and old things and old laptops and everything. I'm also a computer network enthusiast. I take part in HK3, which is a non-profit organization from Hradec Králové. We build networks, and now let's introduce our last colleague.
And our last colleague, who unfortunately didn't make it to the event, but quite important for us, Andrea Manzini. I am so lucky to have him in Security QE because he's a brilliant engineer with lots of experience, and he's the main author of the project we are presenting now. So shame he couldn't join us, but he helped us create this presentation. And if you have any inquiries regarding any technical topics, then feel free to reach out. And I've been assured that he'll give you a response. So that's Andrea. And we've also learned, after over 2 years with Andrea and my team, I've learned that Andrea means Ondra, but in Italian. So when I say Italian Ondra, I mean Andrea. Okay, so first, an introduction. What is binary coverage all about? Well, in short, measuring code coverage of automated tests. At SUSE, we have many tests, hundreds of them. And when you have an update of, say, Vim, we have tests which are trying to use Vim, using some abilities, and trying to break it. Those are automated tests running every day, thousands of them, basically. And code coverage means how much of the application are you actually testing? It rarely happens that you cover the entire application, but you have no way of measuring it. That's where the code coverage project comes in. How much code you are actually testing. So, Einer, okay, this is broken. Je tam zoom? Není. Well, it's supposed to say binary program. Imagine you have a binary program. It's made out of many elements, basically functions, and you write your test suite. Why is it broken? Oh, well, fonts. You have a test suite, which is designed to poke into the application, try different things, and test the functions. But it so happens that in this, particular case, you only test part of the binary. And the test says everything is A-OK. But in reality, when you run it in production, it could happen that the untested part of the program fails, which is a bad thing when you push things into production. So here is a more concrete example. Let's say you have a program. We've written this. Well, AI had helped us write this simple utility we call string utils. And you see the usage. You call the binary. You specify an operation, reverse, palindrome, blah, blah. Then you give it a string, and it does something with the input. For instance, you can call string utils uppercase hello, and it converts the string into uppercase. Very simple program. You can reverse the string, of course, or you can use the SUSE cipher, basically shift the letters. Then we write some simple Python script, which is designed to run the string utils binary and check if the output is what is expected. Basically, it tests the thing.
First off, I've been told that we have another microphone here. I know, but it isn't wired for the room, so you won't hear me here. That's why we don't use it. And secondly, you don't have to go so fast. You have time.
Okay, so I'm rushing. Okay, we have a simple Python PyTest script. The top is not really important, but what is are these functions. For instance, test reverse. It calls the string utils binary and gives it reverse and hello. And the output should be ole. If this passes, Python says, okay, let's go, continue. And if it fails, it tells you that it failed. So then you have palindrome, means if you when you read the word from back to front and front to back, it should be the same. So that's a palindrome level, of course. So output should be yes. Palindrome no, world is not a palindrome, so it expects no. That makes sense. So when you run it, it says everything passed. But if you remember, we are testing these parts of the program, but we have many more operations which we haven't tested. So we are missing test for vowels, uppercase, and the SUSE cipher. That could pose a problem when you push the update into production. Somebody uses this. What if an update breaks the SUSE cipher? Then, you know, you're in deep shit. This is where the binary coverage project comes in. Here you have the URL of the GitHub repository. How does it work? It uses Intel pin. Okay. And Ondra, so I stop yapping that much, Ondra will explain how the thing actually works.
All right, great. I hope everybody can hear me on the stream also. And so now let's get into Intel pin. So Intel pin, basically what it does in our case, it can do much more than what we use it for, but we just take small part and use it. It can insert our own code, our own things to do into a running binary on the fly without needing to recompile it, change its source code, and have to do all this hassle around it. In our case, it collects runtime information. We will get to what information specifically later. For example, function names and stuff like that. And as I said before, it operates directly on compiled binaries, which means no recompilation, which is great because we do not want to recompile everything. For example, your own project, you compile 20, 50, 100 source files. It's fine, you can just recompile it, whatever, doesn't matter. But in our case, in our scale, in SUSE we build thousands of packages, some of them smaller, some of them quite large. For example, Nginx web server. It's quite a complicated binary to build, just the building process, and then also we support multiple different code streams, multiple different architectures. So that would mean quite a lot of processing power that would be, I wouldn't say wasted, but it's not really viably used. So that's why we wanted to use Intel Pin. Unfortunately, it is not open source, which makes us quite sad, because we would prefer it to be. For example, the whole binary project, you can find it on GitHub, you can submit a merge request, you can file an issue, you can contribute to Intel Pin. You unfortunately cannot. From all the things we have explored, this is probably the best one to use in our specific case. We'll get to it a bit later. So, sorry?
One more thing to say regarding Intel Pin. We are not sure what the future holds for it, since Intel had some layoffs. So we are a little bit afraid that it might, stop getting more development. We'll see. Maybe we have to find a replacement.
If you really want, you can try this mic. They will hear it on stream, but you have to speak loudly for the audience, I guess. Or that's okay. That's how it works. We've been told. It should be just on. So how it works in our case, I will show you a live demo later, but now I will go all over the steps which we do, and you will be able to see. So firstly, we built our function tracer. That's our own C++ written code using the Pin library. In simple terms, it runs, our own function runs in front of executing each image or each function in the binary, and then logs, I am here, I have called this function, I've been called by this, and so on, and then continues with the function. So basically, for example, you have function to combine two numbers, if I will be using very easy examples, and our code, this function tracer, will log it before it's actually executed. So yeah, as I said, it gets injected into the running library. It collects runtime data, which is all the logs you will see in a short while. And then it saves it to a file or multiple files, and then we analyze it. We use Andreas Go program to parse all the logs from the Pin tool, or the Intel Pin library thingy. It generates two things, or three things: CLI output, to just see what we called, what we didn't call. Then it generates HTML outputs, which are pretty, have colors, have green and red, and have big numbers. And it has dark mode also, dark mode. And then generates XML files, courtesy of Pavel, our colleague sitting here, which we use in our OpenQA to have pretty overview. So what did we use? As we said before, Pin, function tracer. We have duplicate information here.
Yes.
We would better prepare next time. And CMD, the Go binary for generating results. And also, we will show you, we can wrap a binary, and that's a key part in how we use this project for ourselves. So let's get to the live demo. We will compile our stuff, we will initialize the setup, we will run the tests, and then I will show you different results. So let's get down to it. I have created a demo folder or directory, depends on what port you come from, world. Let me show you, I hope it's big enough, the font. Can it be seen in the back? Great. So I have cloned two repositories, one of them being the binary coverage from Andrea, or the Italian Ondra, and the other one being our Linux Days repo from his repository, just for examples. Oh, right, white team, good point. Great, should be better in the stream and on the projector now. So now let's get into the binary coverage. I will show you the README file here in the repository, which I just use as a good reference. Also to mention, this is only x86. This is only x86 architecture supported. Intel Pin does not work on ARM and other architectures. It has quite specific requirements for GCC versioning and stuff like that. You just have to. Otherwise, it won't work. That's how Intel gives it to you, ships it out, and off you go. Enjoy. So we will just run the script build, which will download and extract the Intel Pin library, build the coverage tool, build our function tracer, which I will show you and explain what it does. And in our case, we won't use the included example, we will use our own. So let's do that. I will build it. So it will download Intel Pin, give us some egrep errors. Now we are compiled and done. That was quite fast. That's great to hear. What we have from this are two things. Function tracer.so, shared library object, which we will give to the pin execution tool, you will see in a bit. And then fun coverage, which is the Go binary or Go program, which will wrap and report, generate reports with. So now, let's start with me showing you the PyTest in our example. I will just have to navigate through this. Okay, so this is the source for the string utils from Emil. It is basically what the function name says, nothing else. It's just plain C. Nothing really that interesting.
This is the thing you've seen at the start,
Yes.
The example. And the PyTest is also what you've seen, the snippet at the beginning.
Yeah, isn't really that complicated. If you see possible seg faults and stuff like that, please bear with me. Neither Emil is a C developer. So let's GCC it. Compiled, and now let's see the help. I will show example. It just works. So in the real world, in our OpenQA testing, we just do this basically. The automation calls program, if it's in CLI, it just sends it some commands over the serial line or SSH and expects some output. And we want to keep this, not change it. This has to stay exactly the same. And in the meantime, we also wanted to run the pin tool and give us reports and everything around it. So that is when the wrapper comes into place. What it basically does, let me show you first how we run it, and then I will show you what actually it does. So, sorry to have such messy, complicated structure of folders, but that's just how we didn't actually architect it that much, but it will get better, trust me. So let's see the help. So we will wrap the binary, string utils. So now, what has happened? The wrapping component has taken the original binary, string utils, placed it somewhere else, and instead of it created an executable bash script with the same name. So if I show it to you, this is it. What this does is it calls the pin tool, which we downloaded in the first building step, does all the necessary things, gets all the parameters, runs the string utils as if this didn't exist, but with pin tool. So from the point of view of an automated test, there is no change, absolutely no change whatsoever, and takes all the logs and puts it into /var/coverage/data and puts the logs there. So what I can do now is just basically do the same thing I did before. I want uppercase Linux days. Oh no! Oh right, another mistake. I didn't read the demo, so I have to. Yep. Sorry, I will just not clear like nothing ever happened. and we're done. So exactly the same thing happened, but let's see. Coverage, data. Now we have multiple string utils logs. All of these are from the pin tool. For example, I don't know, 1, 8, 4, 7. I don't know which one, I don't really care that much. 1, 5, whatever. Let me show you 105. Come on, autocomplete, do something. 04? What the hell? Okay, let's do it. Like so. So this is the output. I will get to where it came from very shortly. This is a quite messy, human unreadable file, which we don't really want to interpret by humans. It's just all the images and functions, what it called, what it didn't call, and from where, and what ID of the thread. So now let me show you the function coverage source, what we made to give to pin to run on each binary run. Inject, that's the correct terminology. So, looks complicated, bear with me. It's not bad. So, this is how to basically init the pin. They have very complicated manuals for everything, how to do this, that. We just, or Andrea just followed it. We don't really need to change anything on that. And the most important thing is this. So, in the binary, before every function or image, multiple ways to call it, we call our own function, which is called image load. That is defined here. This, it's defined here. And what this does is basically logs where we are, and that's it. It just logs it to a file, which I showed you a while ago, and it then just casually lets the function run without any intervention basically. So this is like the core of what we do. This is like the most important thing. We inject this code, and we don't have to recompile and so on and so on. I hope it's making at least a bit of sense. Yeah, here you can see how we log the image and section. And when I show you the file, this is the outcome of it. And as I said before, this is not really nicely human readable. What can we do with this? We need something pretty, something better, something nice looking. So we use the Go thing, the Go binary, which we compiled. Here. And we're not going to wrap anything, we're going to report. So, no, var coverage data and output to home report. Oh, and I also forgot another parameter. Let's see. And let's now check what we have here. Oh yeah, here. Nope, sorry. For some reason it didn't work. Let me check. Oh, yeah, I know. Here, great. Now let's check report. And here, string utils. This is what's important to us. This is the output of all the work we did to get to this point. And here we can see what we called and what we didn't call. So these are the function names for our source code. And here you can see we called some of them, but not all of them. And the big thing, the grand thing of this all is this big number called coverage. And we can say that right now, if I run that, I am coveraging the string utils binary by 60%. 60% of it was called. The other 40% was not called. So to put this into perspective for us, for testing, for quality engineering, if there was some regression, some bug, or something in the 40% that we didn't try, that sparks a problem for us, as Emil described in the start of our presentation. Let me now show you the PyTest we have, which was showed before. I run it. You can see all passed, 100%, great. Off we go, off to the next program, ship it to customer. Everything's great, right? It's green, it's passed, it's 100%. What more can you want than that? It turns out it wasn't really that great. It wasn't really 100% of what we did. So let's see. I will see what we have in data here. So we have multiple things here. I will, just to make it clear, remove all of them and run it again, just because we want it to be clear. So PyTest, and from the point of view of PyTest, as I described before, nothing changed. It called the binary, the string utils, like that. Didn't know really anything, but under the hood, we had our own script, which called pin, and then called the original binary. And now let's generate a report. So, yes. Here, as I described, three things: XMLs, HTMLs, and CLI output. This is the example CLI output. It's quite complicated. It covers a lot more stuff, but for us, we can see here, again, string utils. As I described before, this is not staged. I originally planned to have a different number than 60 because I didn't know which specific functions were called and which were not called in the PyTest and my manual writing. So I will try it again and with some different parameters just to make it a bit prettier. I will just delete everything, close this. Oh no, where we are, here. And try it again. Let's get it back here. I will run it just without anything, just printing the help, not calling any other functions. So now we should have even less coverage, and more of the function names should be red instead of green. So, oh, sorry, one more. I have to remove all them and then do it again. So we have clean directory and then create the report. Great. String utils. Now we have 40. We didn't call as much. And you can see, for example, I think it was 2 uppercase, which we had green before. And if I would now run it multiple times with using all of the stuff, so let's say what we didn't call 2 uppercase and count vowels. So okay, and also 2 of them, and also, let's say, what we didn't call, palindrome. Yes, this is a palindrome. So now, if I create a report, another one, after I clean this, it will combine all of them together, all of the runs I just did, so we should have much better coverage. Let's see, 70. So that's not 100%, but that's better. I hope you're seeing how the coverage changes depending on what I do with the program. Here, let me show you. I didn't reverse it. I didn't call the Caesar cipher, but all of the other ones, green, so that's great.
What Ondra did was run it by hand.
Yes,
multiple times. Usually what you would have is the automated test suite which does the multiple rounds for you, of course. Yeah. So then you have, you call it 100 times, so you test 100 functions in this case.
So just to one more time put it into perspective, or for you to be able to imagine how it's actually used, not just as a small demo. Let's say that we have, for example, MySQL server, which we also test because we ship it to customers, and we wrap it with our pin tool, and then automated this test launches the server, and then some other script works with it, some select, some inserts, do this, that, and that, then exits. We get multiple logs, like thousands of lines or tens of thousands of lines. We aggregate it, and that get a number. So SQL database, it's a very vastly complicated application with many function calls, and some of them being old, some of them new. And the important thing is the number, the percent of how much we covered. In these big examples, it won't be really 100% like ever, because you always have some functions which are actually intentionally not called and there, but you generally understand how you are testing. I guess that's it for the live demo. Do we have time? Okay, great. So, conclusion, do you want the port? Sure. All right, so I will give the port to my colleague.
You get the stick.
I get the stick. Here we are.
Sorry. Okay, so what does it all mean? What is it good for? So what did we achieve by all this shenanigans? Well, we now measure the coverage, and we can improve things. Sometimes you think your coverage is good, but then you realize you are missing some very important functions, for instance, which in turn helps you find new issues and perhaps new bugs which you did not know about in the past because your coverage was not wide enough. And we also generate productivity metrics. We sometimes get asked, how much do you actually test? Well, that was hard to measure.
That how much you test?
Yeah.
It should work. Hope you can hear me. How much you test is the golden question to all QE or QA people in the world. It's basically unanswerable. You cannot say how much you test. And if you say a number, for example, binary coverage in percent, that's great. You know, I do this much of this binary, but that's not the whole picture. So remember, it is a good metric, but you shouldn't base important people or business decisions on it.
Yes, we have an asterisk. Coverage does not equal quality or team performance. I am from the security QE squad. And of course, we are not going to have 100% coverage because we don't care about 100% of the functions. We only care about the security stuff. And we have other teams which dwell into different parts of the program. So you cannot say that, oh, you security guys only have 40% covered. Well, you are doing a bad job. No, it depends really on what you are interested in. So you cannot use these metrics as trying to say how much someone is working and not. So, okay, we have a Q&A section at the moment, but we'll start with predefined questions because we had several discussions about this program, about the binary coverage project, and they've been some questions that had been raised in the past. So we prepared them, and then if you have your own question, you can give it to us.
Also, this Q&A time with predefined questions is a time for you to warm up and not to be shy.
Indeed. So first, why do we use Intel Pin instead of a free alternative? Because there are free alternatives. But, well, the main reason is that performance is poor and features. You can basically write plugins for Intel Pin. Andrea evaluated some alternatives, which we might have to use them in the future if Pin does not get further support. You can see the issue number 59 where it's discussed. What are the performance implications? Well, it has to, do something about the performance because it's doing more computing.
To add to this, this is important in our scale, as I said before. We run tens of thousands of tests every midnight or at night. and a lot of software, a lot of very different software. So one small change, for example, if we would have a 50% performance increase or time increase to run something, for us in our scale, it would mean quite a lot.
Indeed, but it is designed to be lightweight, mainly thanks to Intel pin, which is fast. So we have around 5% overhead, which is more than acceptable. What if a function contains logic branching? If this, else that, you don't test every branch. Well, or you have cycles. So if it has branching, well, it only looks if the function is run, and it doesn't look what branch it took. For that, you have code, debuggers, traces already existing. So this is not the scope of the tool.
Yes, and if you would want to monitor all ifs and elses in millions of lines of code, then you would just get mad from it. It's really not feasible in this amount of software we test and we ship.
True. Next question is, can we also trace the function parameters? As in, you have a function and you can give it some parameters. Pin does support it, but we did not implement it. But if that's what we would need, we can add it to a future release.
If you'd like to, you can submit an issue.
Yes. Are other architectures supported? No, just 32 and 64-bit Intel, x86 and x86 64. There was pin for ARM, but it's only in archives and the older version, which again brings you to issues with GCC versioning. And I don't think it will be available again. So yes, we are stuck at x86. Does it work with other interpreted languages, Python, PHP, Java? No, it's only for compiled binaries, C, C++. Yes, the interpreted languages have usually their own tracing coverage utilities, so it's not really needed in our case. Can you add? This was Andreas' question, and his response was no. Okay, now it's free for all. Do you have any further questions? And if so, just shout. We have to repeat it so it's heard on stream. No, yes.
So the question is why we didn't use, sorry? btrace and dtrace as the alternatives. That is a question that I would ask the Italian Ondřej, which isn't unfortunately here. I'm not sure if he has or hasn't tried those. We'll ask him. But I think he has done quite exhaustive research, so I think he came across it. But it depends on how it works exactly.
It's just to give it more context, Ondřej is the main author of basically the core of the project. So he tried many things and knows about it a lot more. We just added, some contributions to it. Shame we didn't manage to bring him here or have him online. Otherwise, he would answer. So if you have questions, you make sure to write to Italian Ondřej. He assured me that he'll gladly respond.
We had another question back there.
Yes.
Does it work without debug symbols?
The question is if it works without debug symbols. No. Because otherwise, how do you know how the function which you are calling is called?
Let's say I want to use it for browsing. Like I give the program, so it shows me all the functions that I activate for a given input. So I don't use it for testing like you do, but I use it to find which functions were activated by my input.
The question. Sorry?
The follow-up was?
Yeah, the follow-up question, if you can use it to just see all the function names you called instead of actually testing or in your words, that's actually what it does.
Like I meant without the symbols, like you don't know to be used in the version of applications.
Okay, follow-up, if you can use it without debug symbols just to somehow log functions. I think you could. You would perhaps have to create your own function identifiers.
I'd guess so, yeah. But
Yeah.
you already have tools for that. So why would you bend this? It's like scratching or something like that when you have guide or whatever.
Good question overall, thanks.
Yes, but yes, thank you for the question. Anything else?
Pavel is smiling there.
Pavel is smiling. Do you have a question, Pavel? Come on, bring it on. No. Okay. We are slowly running out of time, so the most important question of all, how to contribute? Well, first, look at the repository, Ilmanzo binary coverage on GitHub. First, drop us a star if you like it. That motivates us to pursue it. Then try to use it. Report any issues or bugs or quirks or whatever bugs you, and create an issue. Maybe when I was looking at the demo, maybe you were kind of confused by all the paths and all the binaries. And where does it save the outputs? So maybe that could be improved. Create an issue. We'll look into it.
That's
yes.
what you described, basically.
Yes. Help us improve the documentation. We just have a README, but it's not very thorough. So I guess that could be improved as well. You now see it from a different light. We've spent some time on it, so some things we find obvious, maybe you don't. Try and improve the documentation. If you want to write some code or develop, you can pick any open issue there is and just start building. We'll be glad. And give us general suggestions. Again, in issues or contact us directly. All right, well, that's all from us. Again, thank you. Here is the repository. You've heard and seen me, Emil, Ondřej.
Thank you.
And you haven't seen Andrea, but he helped us very much with the presentation.
Shout out to Andrea.
Hello, Andrea, if you're watching.
Hello. So thank you very much for listening. Thank you for the questions. And we hope it wasn't too complicated, too technical, and too confusing. I hope you get at least something from this. And just to use this free time to shout out, I have another presentation tomorrow at 12 o'clock with Pavel, just 20 minutes about Home Assistant. So if your ears didn't bleed from listening to me, you can try tomorrow.
In Czech.
In Czech.
So may it prove useful to you, and thank you. Bye-bye.
Thanks.